This is Dr. Furushani, and in this video, I'm going to show you how to run a multiple linear regression analysis using Jamovi. Imagine that we have two independent variables that we can also call them predictors. And with these two variables, we want to predict our dependent variable that here we name it as dv. So here we name our independent variables as iv1 and iv2 and dependent or outcome variable as dv. Uh, so, and imagine that we have a research question or hypothesis, assuming that these two variables, these two independent variables, can significantly predict this variable, that is our outcome variable. And we also want to see the direction of correlation or the direction of prediction that you want to see. For example, is it a positive prediction or negative? Like higher levels of these are associated with higher levels of our DV, or higher levels of our independent variables is associated or can predict lower levels of our dependent variable. So for this, we can run the go to analysis section of Jamovi and using like the type of analysis that we want is linear regression. And the analysis also would be similar, disregarding having one predictor or multiple predictors. So simple linear regression and multiple linear regression are literally similar. Uh, but using similar options to have those analyses. And also, another good aspect of linear regression analysis is that it allows you to check both assumptions, statistical assumptions for this analysis, and the main analysis all together in one run of analysis. And I can show you how. So first, we need to define our variables for the analysis and assumption checks. So as we can see, the labels for this box is clear, that dependent variable. So we have just put our dependent variable here. And as you know that in regression analysis, you only can have one dependent variable in each run of regression analysis. And however, here the label for this box is a little bit confusing in Jamovi. So they use the label covariate, but you know that for this context, for the context of regression analysis using Jamovi, covariates actually can mean predictors as well, can mean the independent variables as well. So we put our independent variables in this part that mentioned as covariates, but you know that this is actually your independent variables that are continuous variables as well. Um, so this is for defining our model, and you can see that automatically it shows you some results, but it's too soon to check the results because before interpreting the results, we need to tick some more options to have more comprehensive analysis and also having the results of assumption checks. So here we can just leave it as it is because this part is not relevant to multiple linear regression as we just are running a simple multiple linear analysis with one model of that's one model that is our focus. So we just leave it as it is. But in the next part here also we can just leave it as it is, but assumption checks is an important part because we want that our analysis also shows us the results of assumption checks for linear regression analysis. So the first thing that you need to check is autocorrelation test. That is actually for the assumption of independence that I will discuss and explain shortly how to interpret that. The other one, collinearity statistic, that is another assumption of regression analysis that there should not be collinearity between your predictors, that I will explain that as well when reaching to the output. And normality test that actually is about normality of residual assumption. That is also another assumption that I will explain shortly. And QQ plot of residuals also can be good. It's another, again, like a measure of normality as well that we will explain later, but make sure that you tick this here. And residual plots also is important. This can show you the plot that you need to check two assumptions. One is linearity and another is homoscedasticity. And finally, you can choose either Cox distance or Mahalanobis distance. You don't have to tick both of them because there are just alternative approaches to check the assumption of outliers that they can show you if there is any influential outliers, any outlier that you need to remove potentially, that any outlier that affecting your mediation model. I would always prefer Cox distance because it's simpler to interpret, and I will show you how to interpret that as well. But you can use Mahalanobis distance as well, and if you are confident in and you're more comfortable with that analysis. But my recommendation is checking Cox distance. And also, you need to check if all the main statistics for your main analysis, main results are also ticked here. That, for example, R squared that are essential ones that are already ticked. If it's not ticked by default, make sure that they are ticked. And adjusted R squared is not, and the rest of them are not very applicable for this type of analysis that we are running now, but they can be applicable for other types of regression analysis. And F test also is important because it's actually for the significance of R squared that we can check it through ANOVA F. And I will explain this as well later. And for other parts, like a standardized estimation also can be a good option to tick because it can gives you some information to interpret your effect sizes. And also confidence interval is an APA recommendation that you report confidence intervals for your estimates that you can have it like for both standards and standardized estimates as well. So it's harmless if you tick this one as well. You don't need to change the rest. I see that, yeah, the rest of the statistics are fine. So just these ones that I mentioned here would be comprehensive enough to have a comprehensive and informative output. And now let's check our output and see how the uh, results look like. So as you can see, the output starts in Jamovi. The output starts with the main results of linear regression. But I would recommend that before going to see and interpret the main results of linear regression analysis, it's important to check the results of assumption checks first. Because if the assumption checks show that there is a significant violation of the assumptions, then you cannot trust the result of linear regression analysis. And before reporting or interpreting the results, you may need to do some other measures to fix the assumption violations, and then you can interpret the results. That would be the topic of another tutorial video in our channel. But for now, let's see that how our assumptions look like. So here you cannot see anything about assumption in this table. And but here, this is one of the assumptions that you can see, like the table about Cook's distance that you remember we ticked that. So in Cook's distance table, what is important to check is this part, like the range and maximum part for Cook distance. That shows that the highest possible Cook's distance that was observed in our data is 0.14. So what does it mean? As long as this statistic, like the maximum value for Cook's distance, is less than 1, we can uh, consider this that there is no influential outlier in our data set. And you can see this statistic here is much less than 1, is 0.14. So we can rest assured that the assumption of outliers, lack of influential outliers, is met and we don't have any participants that can be considered as an influential outlier. So the next assumption that you can check that you see that in the output they didn't include coexistence as like the output does not include this under assumption, but it is actually one of the assumptions based on like many statistical table and convention that you shouldn't have significant outliers. So the second assumption is a Durbin-Watson statistic that is for the assumption of independence. That is one of the ways that we can check the assumption of independence, and we can refer to this table. So what is important to check? This middle part, this middle column is important for Durbin-Watson. So as long as Durbin-Watson value, this middle part, that this you see its abbreviation for Durbin-Watson statistic. As long as Durbin-Watson statistic is close to the value of 2, that means that the assumption of independence is satisfactory and it's probably met. It does not need to be exactly true. It can be any value close to 2. Like for example, like here, 2.13 can be like a 1.90. So all of these situations are appropriate, and we can say that this assumption is met, the assumption of independence. So remember, this middle part should be around 2. The next one is collinearity, like lack of collinearity. That is also important to be checked. Collinearity means that your predictors, like this IV1 and 2, should not be highly correlated. And if this, for this assumption, you can check VIF. You can also check tolerance, but I would recommend VIF because it's a more lenient measure to check this assumption. And as long as your VIF values in this table, like this middle column, is less than 10, you can say that there is no collinearity concern for your result. Or you can say the assumption of lack of multicollinearity is actually uh, met. So, and here you can see that it's way below 10. So I can say that this assumption also is okay. And the other assumption is like the normality of residuals assumption, that you can see that I know that you here you have Shapiro-Wilk for that. That is specific to Jamovi that actually give you a Shapiro-Wilk for this assumption that we definitely don't expect a significant Shapiro-Wilk. That is good. We don't have a significant Shapiro-Wilk here. However, this is not the most common way to refer to this assumption for regression analysis, because in regression we are reporting the normality of residuals. Shapiro-Wilk is mostly reported for a normality of row scores or normal distribution. So this is more understandable if you refer to QQ plot for normality of residuals. And what you expect for this assumption to be met is that you expect that the data points are approximately on this line or very attached to this line. But here you can see, although the Shapiro-Wilk result is sort of satisfactory, however, you can see that there are some data points that are not perfectly sitting on this line. And this can show that there is some slight violation from the assumption of normality of residuals for our regression model. Because this is not about the individual normality of your results, it's about the normality of residuals of this regression model as a whole. So not just individual variables. But the interpretation is very similar to normality of raw scores or individual variables, that you expect that these data points should be sitting on this line, that you see that there are some violations here. So this can indicate that we may need to do some other measures like transforming the data and other types of measure that I can cover that in another tutorial video. And let's see the next assumption, that is So this scatter plot can be used to check both assumptions of normality and linearity. For both of these assumptions, we expect to see that these data points are evenly distributed all around the plot, not focusing on a specific part. We also don't want to see some specific patterns or shapes based on the data points, that we don't see any of them. So these are good news for both the assumptions of linearity and homoscedasticity. However, focusing on the assumption of linearity, as long as you don't see a U shape in the data point, that the data points are not shaping a U shape, or converted U shape like this. So that means that the assumption of linearity probably is okay, and it doesn't, we are not concerned about that. Also, you can additionally check the assumption of linearity based on this one, these are figures, like for example, that can show that we can see that there is sort of a linear line between like residuals and your DV, residuals related to your predictors and your DV. And also this can show that individually for your IVs. However, these are can be a little bit strict sometimes, especially when you don't have very strong correlations. So in that cases, it would be better. I mean, the most lenient approach is that you just focus on this scatter plot, and as long as you don't see a U shape or converted U shape, or as long as the data are distributed evenly everywhere in your plot, we can say that linearity is probably okay. There are also some strict ways to check linearity that we can do and check that using the like bivariate correlations that I will explain that in the other tutorial videos about bivariate correlations. So the assumption of linearity we can say is okay based on just this plot alone. And also next is the assumption of homoscedasticity that can be also checked based on the same plot. The assumption of homoscedasticity, I mean, very simple language, it means that there should not be like a very specific patterns or variances in your regression models. But this very simple language, and you don't need even to explain that in your results or reports. But you need to say that whether this assumption was checked or not checked. And for saying that, as long as your data points, if, for example, consider a line here, if you imagine a line next to zero, like what I'm showing here, you expect that the data points are evenly distributed above and below these lines. That is almost the case. So it doesn't need to be perfectly, but almost the same data points above and the same data points below this line should be observable. And also you expect that there are some sort of symmetric patterns above and below these lines. And you can see that almost there is a random distribution of data above and below the lines. So these are good signs for homoscedasticity and can show that the assumption of homoscedasticity is indeed met. And so I would say that this single scatter plot can be enough for the assumption of linearity and homoscedasticity, although you can be like, if you want to be more precise, you can also interpret the next ones as well. But as I said, it's not a very necessary step. So this all we're all about the assumption checks. And now, if we want to ignore the slight violation for the normality of residuals, we can trust our main results, and we now can go and interpret the main results. So you can start to report or interpret your results from this table, especially the statistic for R squared. So R squared here is 0.17. What does it mean? It means that 17% of the variance of your dependent variables can be explained by your predictors together. Like for example, IV1 and IV2 together can explain 17% of variance or variation in your DV. So this is the interpretation for R squared. for like the collective predictive power of your predictors. However, we still don't know whether it is significant or not significant. How we can check that significance of this? This is based on the F statistics. So F statistic that's also called ANOVA is actually a sort of ANOVA, but we run it to check the significance of R squared statistics. So as long as F statistic is significant, that means that you can trust your interpretation of R squared. That means that you can confidently say that now that your IV1 and IV2 together can significantly predict 17% of variance of your dependent variable. So this is good enough for now. Like for example, we wanted it can help actually to test our hypothesis or have a research question. However, it's not specific enough because we still don't know what is the individual prediction for each of the independent variables that we have in this model. And also we don't know the direction of the regression. So for example, we don't know if higher levels of IV1 and IV2 can result in higher levels of DV, or higher levels of these predictors can be associated with lower levels of DV. This is what we can check in this table, in the next table, that is about coefficients. We call it regression coefficients. So in this table, as you can see, we break down the results for each independent variable separately to show that how each one of them individually can predict our dependent variable and show that the direction of the prediction as well. For example, for first independent variable, you can see that estimate means that on a standardized coefficient, and a standardized estimate means that a standardized coefficient. There are actually just two versions of the same effect, but the difference is that you can interpret a standardized estimate like in terms of effect size. Or you can say that is it a large effect, a small effect, or medium effect based on like Cohen's guidelines. But you cannot say that for on a standardized estimate because it can be different based on the measures that you use. So now let's check, but you can see that there is one p-value for both of them. The p-value presented here applies to both the standardized and unstandardized estimate. And also, but confidence interval can be different. Confidence intervals here is for unstandardized estimate, here is for a standardized estimate. And how to interpret that now? Let's interpret it based on the standardized estimate. That means that first we check the direction of the coefficient. That we can see is a negative direction. That means that higher levels of our first independent variable is associated with lower levels of our dependent variable. So that is a negative prediction. So that is the first information we get from this table. Then we also can check the significance of that. So you can see that the p-value is less than 0.05. That means that this is a significant prediction. That means that we can confidently say that higher levels of our IV can significantly predict lower levels of our DV, because it's a negative prediction. What you need to report in your output is you can report a standardized on a standardized estimate. You can report confidence interval. You can report T and p-value, because p-value is actually presented for T to show the significance of this effect. And so you need to actually report the t-value as well. And also you need also to report the standardized estimate for interpretation of effect size. For example, based on Cohen's guidelines, you can consider this effect as a sort of small to medium effects because it's close to 0.30 that is considered as a medium effect. And now our second independent variable that you can see again, the direction. The first thing you want to check is the direction of the effects. You can say for estimate, for either for unstandardized or standardized is a positive effect. And that means that, and also you can see that this is significant. So that means that higher levels of IV2 is associated with lower levels of DV. Or you can say that lower levels of IV2 is associated with lower levels of DV. So it's a very straight and positive regression. That means that IV and DV changing, they can change in the same direction. It's not a negative prediction. So it's different between IV1 and IV2. IV1 is a negative predictor, IV2 is a positive predictor. But together, they can have a significant prediction as well. And again, you can see that this effect is significant for IV2, and you can see that like again, it's almost the same effect size. The standardized effect is 0.23, is close to 0.30, that is a medium effect. So you can see a small to medium or a small effect. And that's all you need to report for the results of your multiple linear regression and to check and test your hypothesis. Finally, if you'd like support with write-up the results and interpretation for multiple linear regression analysis in your research paper, thesis, or assignment, feel free to book a proofreading session using the link in the channel description.